In this video, we're going to introduce some of the ideas of the probabilistic method in combinatorics so that we can prove a claim in Ramsey theory. So what's our claim? For any integer t greater than or equal to 3, the Ramsey number RTT is greater than the floor of 2 to the power of t over 2. What does this mean specifically? That is, we should be able to show that if r equals this floor of t to the power, or 2 to the power of t over 2, then there must be some red-blue coloring of kr that doesn't contain a red or blue kt. Because remember, the Ramsey number is the minimum number such that every coloring has at least a red or blue kt. So in this case, it would say we're not at that number yet. We still have some red-blue coloring that doesn't have one of those. So that's what we're going to try to prove, and to do that, we're going to use the probabilistic method. So we need to introduce a few terms with the probability, or about probability. So we're going to have this thing called a probability space, and that's just a finite set of objects S together with a probability function P going from S to 0, 1. As we go through these definitions, let's talk about what the relevant things are going to be in our proof. If we're looking at a finite set of objects and considering the probability, well, the finite set of objects we're going to look at are going to be red-blue colorings of Kr. That's what we're going to do in our problem. So we're going to have a whole bunch of red-blue colorings of Kr, and they're going to have equal probability. So all equal probability. How many red-blue colorings are there of Kr? Well, there's going to be r choose 2 edges, and then I'm going to have 2 choices of color for each edge. So there should be about a, we'll say that P of S is going to be 2 to the power of r choose 2 for each of these, because again, I have 2 choices of color for each of my edges. So, 1 over that. There you go. And then if you add all those up, you'll get 1, which is, kind of what you want. So, all right. So now we're going to call any subset of S is called an event. And you calculate the probability of an event by summing up the probability of each element in that subset. Also, it should be the case that the probability of everything in S, something in S happening, is 1, and the probability of nothing in S happening is 0. So let's be a little bit more clear with that. The probability that at least one thing in S happens if I pick one randomly should be 1, and the probability of nothing getting picked if I pick at least 1 should be 0. So what's our event going to be in this case? Well, we are going to be interested in red-blue colorings that don't contain a red or blue K2. So that would be our event, would be colorings that do not contain a red or blue, I think I said K2, but I meant KT. So that's the event we're going to look at. We also have this idea of complementary events, and that's basically everything that's not the event we're looking at. And it's going to have a probability of 1 minus PA. And secretly, in this problem, we're not going to start by looking at colorings that don't contain a red or blue KT. We're going to look at the complementary event, colorings that do contain a red or blue KT. And we'll actually get to that later. First, I want to make a note. So if I have something that has a probability greater than 0, what does that tell me? Well, what it tells me is that when I'm taking this sum, there had to be at least something in that sum. So that tells me that A is non-empty. So what are we going to be trying to show? We want to show that the probability that P of A, where A is the event of getting no red or blue KT, we want to show that event has a probability greater than 0. Because that would show that there is at least one thing in that event. There's at least one red-blue coloring that has no red or blue KT. And again, we're going to actually do that by showing that the probability that something does contain a red or blue KT is less than 1. Because if that's less than 1, then when I take the complementary event, it's going to have a probability that's greater than 0. So that's going to be our kind of battle plan coming up. One last thing that we need to do before we jump into the probabilistic method is we need to talk about some kind of addition properties. So the probability of A or B, or maybe both occurring, is going to be less than or equal to the probability of A plus the probability of B. And the reason why, and actually this extends for, any number of events too, and that's because if I take the union of A and B, well, that's going to be everything in A, and everything in B, and everything in C, and everything in D, but then we're double counting a bunch of stuff. So I need to subtract away everything that's in the intersection. Remembering that A union B equals, or at least the cardinality of A union B equals the cardinality of A plus the cardinality of B minus some overlap. That's, of course, going to be less than or equal to the cardinality of A plus the cardinality of B. And then, therefore, if these are all assigned some probability, in this case, all the probabilities are the same, but they don't necessarily have to be, you can similarly see that this probability is going to equal this, except then we would maybe need to subtract away some overlap. So we get this nice inequality, which will help us do the work that we need to. So there we go. There's some basic ideas in the probabilistic method that's going to help us prove our claim. So that's a good place to start.